This is TWiT.
Hey, I am so excited about our guest today. Stephen Wolfram, one of the smartest people in the world. He was a child. I did not know this about you, Stephen, and I hope it's not wrong because I asked AI. A child prodigy at the age of 15. You published your first scientific paper, studied at Eton and Oxford before earning your PhD in theoretical physics from California Institute of Technology at the age of 20. A MacArthur Fellowship genius at 21. Most people wait till their 40s. And of course, the creator of Mathematica, Wolfram Alpha, and the Wolfram Alpha language. It is such a, and the author of many seminal works, not just in physics, but many other subjects. I think cooking, yes?
No, not cooking.
No? Okay.
No, I don't know how to cook.
When is the cookbook coming out?
Deficits.
We want to get you on because this show is about AI. You've been, thinking and working in the field forever. What was that first paper when you were 15? What was that about?
It was about particle physics. In those days, particle physics was the most exciting thing going on, just as maybe people would say machine learning is the most exciting thing going on now.
Yeah.
And there were things that had been discovered, and I was trying to figure out what was happening with them. I have to say, my first paper was not my best. And, it's
only uphill from there.
Yes, right. It's one of the things that was trying to figure out things about what electrons are made of, and I had kind of an idea about that. And I mean, this is maybe a technical point, but I kind of thought maybe electrons are 10 to the minus 18 meters across. Now, I finally think I do have some understanding of what electrons are, and I think maybe they're 10 to the minus 81 meters across.
Wow.
So it's kind of a flip around in the exponent, which is, anyway, so yes, that was my first paper about particle physics.
No one should peak at the age of 15. You should be grateful that you did not.
Indeed.
Right?
Yes.
It would be very depressing to have peaked at the age of 15. You said something interesting, though. First of all, you called it machine learning, not AI. Is that a conscious choice?
Well, AI has been harder to define. I mean, back when I started building big computer systems to do kind of science type things, which was late 1970s, people were saying at the time, oh, when you can do math by computer, then we'll have AI. And then the goalpost moved, and that wasn't what AI was supposed to be about. So it's I think machine learning is a bit more, AI has sometimes been the thing which is just a bit out of reach to computers.
Yeah.
Which is makes it a little hard to define. And now we've got AGI, which is again just out of reach to computers type thing. I don't think it's a well-defined concept. So yes, I think the thing that one could sort of distinguish is things which are sort of defined computationally. That's one whole branch of effort that I've spent a lot of my life on, and things which are specifically built using things like neural networks and kind of the traditional tools of machine learning, and that's a different branch that happens to be doing really well right now. I mean, I started playing around with neural nets back in, I think 1981 was the first time I tried to simulate a neural net and didn't do anything interesting. And I thought for years, nothing interesting is going to happen with neural nets. And then, 2011 comes around and really interesting things started happening with neural nets. I still think, even now, I'm really curious, why do the things that happen with neural nets actually happen? Why do they work? And that's much less clear. And I've tried to figure out some things about that from a science point of view recently.
Yeah, I remember your article in 2023, which was turned into a book, talking about LLMs and why they don't do math, and proposing that maybe they should pair with Wolfram Alpha to let the Wolfram Alpha do the mathematics. Why is Wolfram Alpha good at math? How does Wolfram Alpha work differently from LLMs?
Yeah, so I mean, what we're doing is to compute using definite algorithms that we explicitly write. And taking data from the world that we've kind of gone to the trouble of explicitly curating. Sort of the big idea of machine learning is You give the machine a bunch of examples of what you want it to do, and you hope that it will kind of figure out what to actually do in any particular case. So it's not the kind of thing where you're setting up sort of this rigid structure that the thing is going to follow. And for some things that we do as humans, kind of doing it roughly right and doing it across many different situations is exactly the right thing. There are other things that we want to do where we need to do sort of a precise computation. You need to build up the tower very tall, and that's something that's not a thing that kind of the neural net kind of machine learning approach is really so suitable for. I mean, it's like if you want to get it 80% right, then using machine learning is a great thing. If you want to get it 100% right, then using machine learning is usually not the right thing. That's a case where you need to have sort of this precise sort of tower of functionality that you build up.
Is that because of the probabilism that large language models have been built on and machine learning is built on versus the kind of determinism of the explicit programming you talk about?
I think that's one way to put it. I mean, I've been trying to understand what is one actually doing when one is doing machine learning. In other words, you give a machine, 10,000 pictures of cats and 10,000 pictures of dogs, and then you say, now I'm going to show you a picture. Is it a cat or a dog? And then you showed a picture of a dog in a cat suit. What's it going to do? Well, what it tends to do is something that is fairly similar to what humans do in a situation like that. The whether it agrees with what humans say will be, it very often will. Why does that happen? We don't have a precise sort of definition of why that happens, and what the boundary between catness and dogness is for the machine. But I think this question of the analogy that I've found useful, that's sort of come out of some science I've done in this area, is let's imagine that your task is to build a wall. Well, one way you can do that is you make these very precisely engineered bricks, and you set them up in this very kind of organized way, and you've built this wall, and you can keep building it, and you can keep building it very tall. Okay, that's plan A. Plan B is you see a bunch of rocks lying around on the ground, and as you build your wall, you find a rock that's roughly the right shape. You stick that one in, you keep building that way. That second thing is pretty much what machine learning is doing. When you train a neural network, what it's doing is it's finding these kind of lumps of computation that happen to fit into what the training looks like and so on. And so it sort of puts that rock into the wall and keeps building. And it's something where you can build the wall to a certain height just with these randomly shaped rocks, but it's not something where you're going to be able to sort of systematically build it up very tall. I think that's perhaps a way to think about what's going on. But in the end, it's that kind of machine learning is getting things roughly right, and that's a big achievement. In many domains, getting it roughly right, writing that essay that makes sense is great. You can't say that essay is precisely the right essay. It's just, it's an essay that makes sense. And I think that's the, it's the distinction between what needs to be precise and really built up many, many steps, and what needs to happen sort of roughly right.
The ML is stochastic. So while 2 + 2 is always 4, in the LLM world, it might be, whatever, 5, 4, 6, 3. But there seems to be, and you've worked with cellular automata, which I find fascinating. And I think for a long time, the thought about, like Conway's Game of Life, the thought about these was there would be emergent properties that would come out of this. That seems to be what's happening with LLMs right now, or no?
Somewhat, yes. I mean, so just to explain that thought, I mean, the big thing that was, to me, a huge surprise from the early 1980s is even if you have a really simple program, like something that's just sort of one line of code, that you can specify it by some very simple rules about, black and white squares or something like that. Even if the setup, the rules are really simple, the behavior that can emerge can be really complicated. That's something that's very surprising to us because we're used to, we're doing engineering. We want to make something complicated. We have to go to lots of effort to make it complicated. What we discover is in the computational universe of possible programs, even a very simple program can do very complicated things. And that's a big deal for one's intuition about how nature works and lots of other kinds of things. it's also a part of the core of what happens in machine learning, but I think the path is not quite so direct. I mean, this question of when you say it's sort of an emergent thing, I think that's true, but it works in a slightly different way. So, I mean, the thing that is surprising about machine learning is that the kinds of decisions that it makes seem to more or less agree with the decisions that we humans make, like the is it a cat or a dog type thing. It seems to, surprisingly, more or less agree with the way we make those distinctions. And I think there's sort of a question of why that happens. And I think the probable answer is because its architecture is fairly similar to the architecture of our brains. And so it's making those distinctions in the same kind of way we make those distinctions. Now, it turns out that to get to the point of being able to train the thing from examples, you do need a bunch of this same kind of emergent behavior that you see in things like cellular automata. But that's a more sophisticated part of the story. I mean, I think the most significant, the sort of zeroth order effect is that what the neural nets do seems to sort of align with what we would typically do in similar circumstances.
And yet, the thing that, or the goal, it seems to me, for these would be for them to do something more than a human could do.
Well, I mean, there's a matter of scale, right? Like I'm, right now, I'm trying to use LLMs as a tool to study something that basically needs me to read, 500,000 papers.
Right.
I'm not going to read 500,000 papers, but can I extract the essence of those things and, in a human-like way, as if I was reading those papers? And the answer is probably yes. And so that's an example. Now, there will be things that I can, there's a lot of leverage I can get from being able to do that. Is it something qualitatively different from what I could do? No, not really. It's just a matter of scale.
So the thought that maybe an AI could come up with a way to do nuclear fusion that we haven't thought of, or fold a protein in a way that we haven't thought of before, or create a new material, is that out of the question?
Well, the thing to understand is doing original things is easy. If you have a sequence of random numbers, that sequence of random numbers will be original at all stages.
Yeah.
The question is, does it align with anything you care about?
Valuable versus original, yeah.
Right. And I mean, so now the question is, could you come up with something that's really good by, for example, noticing that, across, the 100,000 papers that relate to different approaches to nuclear fusion, there is this theme that you can extract that lets you see what to do. Yes, that's perfectly possible.
A human could theoretically do it, but maybe an AI is more likely to do it, given that there's a million papers.
Yeah, and I think that the human plus AI is the best alternative. And I think the thing to realize is what ends up happening is, AI is an automation mechanism, as far as I'm concerned. And the way that tends to work is somebody has to say, what do you want to do? And then the automation mechanism can go try and do it. But if you don't know what you're trying to do, there's no place to start. And I think, the AI that's just incredibly, it's learned a lot of stuff, but it's just sitting as a box on your desk. It's like, well, what is it going to do? There has to be some, well, I want this to happen. And, we humans have lots of things where we say, I want this to happen. Now, you could ask the question, if you just got a lot of AIs hanging around, won't they kind of spontaneously say, I want to have this kind of thing, this thing happen? And at some level, that is, you could look at what's happening in the AIs that already exist in the world, and you could kind of probe that, and you could say, it looks like this AI wants this or that thing to happen. And there's this whole sort of civilization of AIs that's already starting to exist, that's sort of separate from human civilization. And at the beginning, it seems like that's a really weird thing, and it's a really scary thing that these AIs could be off having their own, their own civilization independent of us. But the thing to realize is there's a really good model for that we are very familiar with, which is the natural world. The natural world is off doing all kinds of complicated things. It just does them. It's, we live around it, but it's not, it's not something where we're all freaked out because the natural world is doing things that we don't know about, we don't understand, et cetera, et cetera, et cetera. So I think that's kind of the picture of where I see things going with the kind of the civilization of the AIs versus the civilization of us humans.
I love that. And I know what you want to ask, Paris, and I know what Jeff wants to ask, but I'll let you go ahead. I won't take your question, but I know where we're going here.
How do you define AGI?
I know it. I knew you'd say that.
The minute you said that, I knew. I was like, God,
One of us was
God.
going to ask it.
And specifically, there's two questions. One, how do you personally define AGI? And two, do you think that there's this common definition or like a shorthand of AGI that goes around of, superhuman intelligent AI that could replace humans and outpace us at tasks? Do you think that that's feasible?
Well, okay, I think AGI is a really mushy concept, and I think
Yes.
it is the emergent concept from AI, which was always a mushy concept. So it's this thing about, can you make something which does everything a human does? You'll always be able to find things that that the thing doesn't do. Like it's not mortal, or it doesn't get flu or something. The only thing that does exactly what a human does is a human. Yeah. And, you'll always be able to find some place where you can kind of find the magic thing that is the unique thing left over for humans. My first comment. My second comment is that I think that, in the end, the AIs can get very powerful. They can do all sorts of elaborate computational things. Lots of, I've spent a large part of my life studying what sort of simple programs in the wild can do. And they can do amazingly sophisticated things that are probably just as sophisticated as things happening in our brains. The issue is that there's a question of, do those things align with anything we care about? I mean, there's plenty of things that happen in the natural world that are, in some sense, computationally more sophisticated probably than what's happening in our brains. But it's a question of, are those things where we say, oh, that's human-like intelligence-like stuff? And the answer is not usually. I mean, we sometimes say, the weather has a mind of its own, but that mind is fairly different from a human mind. It's unpredictable, it's complicated, but it isn't sort of human aligned. So I tend to think that the story ends up being that there is this kind of computational resource that is the civilization of the AIs, and there's how we interact with that, which tends to be things where we say we want to have this happen, and then we get AIs to do that. And sometimes things will just happen because that's what the sort of the natural course of AIs leads to have happen. So I think it's sort of the idea that something happens that is superhuman. We have superhuman things happening all the time, either in nature or in our computers. And a lot of things I've studied in my efforts in science have to do with even very tiny programs that in a sense do superhuman computations. But we look at them and we say, that's interesting. Sometimes we say, I see the significance of that and it's really cool. And sometimes we just kind of shrug and say, well, that's computationally sophisticated, but it's not something I care about.
You, of course, have written a lot about the computational paradigm. I'm wondering if there's any intersection between that and what we're calling machine learning or AI today, or are they separate domains?
No, I think that the way I see a lot of what's happening with AI and machine learning right now is providing outstanding kind of linguistic interfaces to things, sort of humanizing the way that one can interact with things. The question is, what's behind that? And the thing that we have been able to do with computation is build these kind of tall stacks of capability. And that's something that, if you went back 300 years or so, people were still talking about natural philosophy. The idea of kind of mathematical science hadn't really started off. And, if we'd gone straight from natural philosophy to today, there wouldn't really be a back end that we could talk about. It really would be, it's just this human-like thinking, this kind of linguistic interface and so on. But right now, we can actually compute things. We can build these kind of tall towers of computation. We can work out things that involve, millions of steps, where each step has to be precise and so on. And I think that's what I've spent a large part of my life building the tools to make that possible. And I think the thing that's really kind of interesting right now is, we built that for human users. Now we also have lots of AI users. turns out that because the AIs are using this kind of linguistic interface that matches humans, that the things we did to make what we built suitable for human users are the exact right things to have done to make it suitable for our current AI users, so to speak. But
Oh, that's so exciting. That's amazing.
Right, the emerging thing is you talk to the AI, but the back end is a computational kind of thing. And, we built Wolfram Language to kind of have this sort of computational representation of the world where you can do precise computations, where you can have precise knowledge, you can build things up and so on. And I think, my vision of the future is that there is this layer of kind of linguistic interface, and then there is this kind of computational bedrock, this kind of computational knowledge bedrock. And that the thing that we don't yet know really that well is we only have sort of the coarsest ways to interface between that sort of linguistic layer and the kind of computational bedrock. But I think, for example, the idea that, we're going to train the LLM to learn, what the millionth digit of pi is or something. This is not a particularly good idea.
Yeah.
It's what in an LLM, you're taking knowledge, grinding it up in some way that we don't understand very well, and where is that million digits of pi? Is it in the collective, features of 1,000 weights spread across the neural net? It's a mess, and it's not kind of the right way to implement things. Just as if we were, if we had all of our computer infrastructure, but there were no actual computers. The computers were, as they used to be, humans. And we said, okay, we want to run a program. Let's get a human to run the program. Turns out humans aren't very good at running programs in their minds. And, that wouldn't work very well. So we have these, we have machines to run the programs. And that's something where the humans define what the programs should do, and then the machines run the programs. And I think that's the same sort of direction that we see, happening in what's happening with kind of the current version of AI.
Yeah, in fact, if you want to get an AI to do mathematics, you say use code, and then it can do it. That's the interface to a computational system.
Yes.
Then it can do it, and it does it quite well.
Hopefully using our tech. It works well using our tech.
Yes. So, and of course, that's one of the things people are talking about a lot these days is replacing human coders with AI.
Well, you have to understand what's really going on there. I've spent a large part of my life as a language designer. Yeah. What does a language designer do? Well, a language designer is trying to take sort of the things that humans want to do and define primitives in a computer language that let the human do what they want, specify what they want in as good a way as possible. The approach most people who've designed languages have taken is that I'm just going to have this very small language, then I'm going to rely on people to build up libraries that do specific kinds of things. I've done the crazy thing in my life of trying to build sort of an integrated language that does everything, that sort of coherently defines sort of everything in a computational way. And for me, the main thing we're seeing is people, what in our language would be, a line or two of code, because we've defined all those operations integrated into the language, people have been used to using, in many cases, sort of low-level languages where it takes a giant blob of code to do this thing. And so then they see that, yes, the AI can write that giant blob of code. For me as a language designer, it's like that giant blob of code just shouldn't exist.
It shouldn't exist at all. Yeah.
Yeah, it should have already been defined because that's a blob of code you repeatedly want to do. That should have been defined as a primitive thing in the language you're using. So, I think now having said that, the idea that you can go from sort of a thing that you just talk about linguistically to something in code that actually works particularly well with our computational language because it's sort of the closest to being able to deal with things that you just talk about, like cities or videos or whatever else. And so what, we released a product recently that's our notebook assistant, where it's kind of remarkable the extent to which you can just be blabbing along and saying something kind of vague, and it will try to get sort of to code that is the closest code it can find to what you thought you were talking about. And it's quite interesting because it kind of crispens up your idea. You're kind of saying something vague. it says, well, let me respond with this precise piece of code. And sort of the whole idea of our computational language is it's a language that can not only be written by humans, but can also be read by humans. So in a sense, what's happening is the AI is responding and saying, well, the thing I think of that I'm reminded of by what you're saying is this precise computational thing that you can then respond to, and so on. And that seems to be a very powerful way to do things.
Are you using your own models for that, your own LLMs, or?
We're using mostly other people's LLMs, but there's a big sort of layer of other technology around that is essentially doing things like dynamically prompting the LLM with using computation, using RAGs and things like that to be able to provide, to be able to say, given that that's what the human said they wanted to do, hey, LLM, you should know exactly this and this and this. And then the LLM can kind of fill in the details. And then on the back end, we're also kind of cleaning up what the LLM did to provide sort of the best possible code. And that it works well. But it's worth realizing, and I think this is a general feature of a lot of what's going on with LLMs today, that the harness is pretty important. I mean, we had built an early version of this 18 months ago. It didn't work that well. As we tightened up the harness, so to speak, it started being really useful. And the LLM is an important component, but the harness is also important.
What do you wish for next? I'm gratified to hear you say, to kind of reject the hubris of the human, thinking that the goal is to replicate and beat us. It's to do these amazing things that it can do. Jan LeCun said in The Guardian, I think 2 weeks ago, that teaching it reality, that when the ball falls off the table, it doesn't go away. Jensen Huang talked about training the digital twins so that it knew how to deal with that reality. That's one view. What do you wish for in next developments? Because every AI company now is coming out with this next version that's just that much better, that much faster. Where's the leap that you wish for?
Yeah, I mean, I think you have to look at the history of AI, machine learning, and so on. There have been a series of kind of jumps. You know, for a long time, neural nets didn't do anything terribly interesting. 2011, they started doing image recognition, then, speech to text and so on, then language generation. And actually, image generation came a little bit before language generation. And there are these kind of thresholds. And my suspicion is that, if you look at, for example, image recognition, things haven't got that much better in the last 15 years. It's incremental improvement. There is this moment where you kind of get over the threshold. It's kind of like, I think for language models, it's a little bit like what I think kind of happened with the telephone. People knew that in principle you could transmit speech over copper wires or whatever, but nobody could understand what was being said at the other end of the phone, so to speak, until Alexander Graham Bell sort of found some hacks that made that work. And suddenly it's like, oh yeah, that sounds like speech. And I think that's sort of what happened in the large language models. It got to a point where it reached a threshold where it's like, yeah, this is basically working. And I think we'll see that in a bunch of other areas. I mean, the area that's sort of an obvious one is the kind of, as you were alluding to, the sort of the real world, robotics, common sense, kind of, I drop this, it falls, that kind of thing. And I don't see any reason that won't happen even fairly soon. Will that be significant in the world? Absolutely, that will be significant in the world. There are all kinds of things that have been, a human has to do that involve sort of manual dexterity and things like this, where it will suddenly be the case that yes, we can use AI to do that. In terms of, on the intellectual side, I would say that the thing I guess, one thing is the on-ramp to computation for people. The idea that you can kind of, for every field X, there's sort of a computational X version of that field, but can people get there? Can, the archaeologist be doing computational archaeology? Well, they say, oh, but I can't program. Well, that's not necessary anymore. You can use the LLM to get to computational language. You can read the computational language. You can be off doing your computational archaeology. So I think one of the big sort of trends will be towards sort of computational X for all X, so to speak, and people really being able to get there. And you don't have to go to the druidic specialized programmers to get the code written to be able to do your computational X. I think that's another piece.
For
I'm
anybody who's
also-
ever used Wolfram Alpha, that is the amazing moment when you type in natural language and get such amazing results. Is the Notebook Assistant kind of the next generation of Wolfram Alpha?
In a way, it's a little bit of a different thing. I mean, Wolfram Alpha I view as being sort of the drive-by answer your question type system.
Right.
You type in a simple question, you get a computed answer. What the Notebook Assistant is trying to do is to set up the sort of the bricks of computation that you need to build up whatever you're trying to do. So it's not just trying to say, here's the answer, you're done. It's trying to say, here's this thing that is a brick, a tool that you can then build on and continue building up. So I think the way I see sort of the future of things like software development is the first thing you have to do is to imagine what you're trying to do computationally. And that's the thing, they don't teach that in computer science school, how to sort of think about everything computationally. But I think that's a super important skill, is like, how do you conceptualize what you want to talk about in a computational way? Once you've gotten some distance towards that, then you can ask our Notebook Assistant, it'll write a piece of computational language code, that'll do a piece of what you want. You take that piece of computational language code, that becomes a component that you can then start building up from to make the larger thing that you want to build. I think that's sorry. See, that's a human feature, not yet emulated by animals. Although I'm sure they could learn from.
Actually, you know, it's interesting because more and more people are finding that LLMs, if you push them long enough, they start to kind of decline, almost physically decline in their ability, which I find fascinating. This must be for you a vindication of the computational paradigm in some ways.
Some ways. I mean, I think that this ability to let more people into the computational paradigm, that's a very important thing. Yeah. That has not yet played itself out. That will play itself out over maybe the next decade or so. And I think people haven't, you know, that's still an emerging realization, so to speak.
More to that. I'm curious, since you've lived in this world and developed this world for a long time, suddenly when LLMs arrive, everybody says, oh, hell, this is AI, as if that has arrived fresh. What's your reaction to society's reaction to, since ChatGPT's release? How have you seen in just people talking in media, in companies, how do you sense that?
Yeah, I mean, it's interesting that this was a moment of consumerization. I mean, it's just like with computers in general. I mean, people, you know, I started using computers when I was a kid in the 1970s, and most people were like, computers, who cares? You know, maybe they're in the back end of something, doing some, you know, bank processing thing or whatever, or figuring out how to launch rockets, but I don't care about that. And then, you know, the personal computer comes out, and people discover things like word processing and games and so on, and suddenly it's like, oh, we really care about computers. I think that was sort of the ChatGPT moment, was the one where people could see that there was this. I mean, by the way, nobody knew ChatGPT was going to work, including the people who built it. I mean, it was really, you know, it's like, at what point? I mean, you know, I'd been playing with language models and sequence prediction and so on. None of that stuff had been terribly interesting. It was, you know, it was a thing where, for whatever reason, and we don't understand why yet, maybe we one day will, suddenly we got over a threshold, you know, some number of billions of parameters. It's like that was enough. That was human-like enough, so to speak. Now, you know, that scale is probably determined by something to do with us. Like, we humans have about 50,000 words in our typical languages. And we have 100 billion neurons in our brains. You know, that provides a definite scale. If you wanted an AI that would be like a dog, for example, in its linguistic capabilities, let's say, you probably need a much smaller LLM, but we wouldn't be as impressed by it. So somehow the size of the LLM, you know, the size of the system was such that it was sort of matched enough of what we need to be impressed by that that we got to that point. You know, by the way, one thing to just say as sort of a side comment, you know, one thing I've been curious about is, let's say we had, you know, 1,000 times as many neurons in our brains. What might we be able to do? What's kind of the next level of sort of intellectual capability? It's just like, you know, Cats and dogs, well, dogs at least, a few individual words, fetch, sit, whatever else. They deal with that. We humans, the big invention of our species, I suppose, was human language and this idea that you can put together an infinite collection of sentences by using all these different words. So a big question is, what happens next? If we could go beyond that, what's the next level of sort of abstraction and sophistication? That's an interesting thing to think about, but you also are stuck kind of thinking, well, if I was the dog, could I really understand human compositional language? And is it the case that there's something bigger? There undoubtedly is, but maybe it's something that just isn't a fit for us. Just like the natural world has lots of things going on that we don't understand except through this sort of bridge of natural science. But I think, in terms of people's reaction to ChatGPT, I think the thing that, a lot of people were like, it's magic, this magic has happened, there's going to be more magic. This was such a surprise. Necessarily, there will be many more surprises. I don't think that's, people always think that when there's a technological surprise, they always think it's not going to stop here, it's going to keep going. But it doesn't always keep going. In fact, it usually doesn't keep going. It usually is, that was the surprise. One got to that sort of threshold level, and then the question was, well, okay, I was a little bit surprised by this, people saying it's magic, and then it's like, well, how does it work? Oh, it's this AI thing, it's this neural net. And I started thinking, well, can I actually figure out some idea of why does this work? And what I realized is, there's at least a picture of why it works. And it's this, and it's something that in a sense was a feature about human language and human understanding that maybe we should have understood thousands of years ago, which is, people have known about grammar of language, that, you form sentences in English having, noun, verb, noun, and so on. But the kind of, that structure of grammar doesn't tell you whether the sentence is going to be meaningful. There are lots of sentences that go noun, verb, noun, and they're completely meaningless. What I sort of realized is that when the LLM is kind of looking at, hundreds of billions of sentences, it's seeing sort of patterns, not only of the noun, verb, noun type, but of this is a pattern of words that makes sense. And that's sort of the big thing that it sort of statistically learns. People were very surprised at the beginning, for example, that LLMs could do logic, that they could kind of make logical conclusions. And you realize, well, how was logic discovered in the first place? Well, presumably Aristotle went through and just heard lots of people giving speeches and sort of identified these are the patterns of speeches that make sense. And then those became syllogisms and they became what we now think of as logic. And I think the LLMs kind of learnt it the same way. And so, in a sense, one of the things that was sort of interesting to me was people sort of say, it's magic. And you realize, well, actually, it's not such magic. There's probably a thing that actually is telling us an interesting piece of science that maybe we should have learned a long time ago. That's sort of at the core of why this can possibly work.
That is also a big part of your book. What is ChatGPT doing, and why does it work? Very provocative. Every time I talk to you, Stephen, I feel guilty that we are using brain cycles that you could be using much more advantageously. I want to thank you for spending time with us and encourage everyone to go to wolfram.com, Stephen's site. It's a great entry point. There are books there. There's links to the new Wolfram Alpha notebook, which I think is fascinating. I'm going to sign up immediately. And I really appreciate the time. You've given us so much to think about. I really appreciate it. Thank you, Stephen.
Lots of cool questions.
Yeah.
Thank you.
Yeah. Have a great day.
Thanks.
Thank you. We'll put this out later in the day. It will go up immediately. We'll send you, if you like, we'll send you some clips if you want to give them to your social people and so forth. You can pass them along.
No, this was
Thank you.
Yeah.
It's always a pleasure to talk to you.
I'm a bit long form. I'm so used to just yakking on.
That's what podcasts
Stephen,
are
I would
made
talk
for.
to you for 4 hours.
Yeah.
I just, again, I'm sincere saying I feel guilty taking any of your brain cycles.
You're very welcome to them. Anyway,
Thank you so much. It's a real pleasure.
Thank you.
We'll have you back in a few months, and we can talk more about this because you've immediately brought up all of this stuff I want to think about. So it's great. Thank you.
Cool stuff.
Really appreciate
Right.
it.
Nice to meet
Thank
you.
you, Stephen.
Nice to see you.
Nice to meet
Take
you.
care. Hey, it's Leo Laporte. I hope you've enjoyed this little clip from our programming at TWiT.tv. For more, visit our website, TWiT.tv, or subscribe in your favorite podcast client. There's also a link somewhere down there.
I'm not a human being.